We're proud to have Aaron Santos here, the author of How Many Licks and How to Estimate Damn Near Anything. So Aaron is a local Ann Arbor resident. He is not only an author, but a physicist and also an occasional actor and director. So he's currently out doing some research here at U of M. Just to give you a little bit more background about Aaron, he attended MIT where he got his BS in physics. After graduating, he taught physics and chemistry in the Boston public school system. And then he attended Boston University where he actually got his PhD in physics. So we're in the presence of a very smart man. So like I said, currently he is studying at U of M the various nanoscale systems. So maybe you can expand on that a little bit. And then without further ado, just please help me welcome our author, Aaron Santos.
You guys all hear me without this? Or is it? Yeah. Okay. Since I don't know what to talk about that. Lindsay, can you hear me? Is the camera going to be able to pick me up fine? Or should I use this?
Maybe use that. Yeah. Sorry.
Right, I guess I will stick with this then. First of all, thank you all for having me. It's an honor to be here. But I have to say I'm a little bit nervous because this is kind of a new experience for me. I'm not really used to the whole author thing, and I haven't really given very many talks on it. So this is a little bit of an experiment for me. And it's not made easier by the fact that the book that I wrote is essentially a book of math problems. So trying to talk for an hour or so about essentially just doing the math that you all hated in high school, it's really hard to make that interesting. So I spent the last 2 weeks really trying to find a way to make this entertaining for you guys. So toward that end, I'm going to talk a little bit about, first of all, why you would want to do things like approximations, and why would you want to calculate things. I'll tell you a little bit about one method that I use in the book to show how to approximate just about anything, and then I'll give you a few hopefully fun examples with that. So I was when I was putting this together, I was thinking, why did I want to write a book on this? And what are the reasons? What did I want people to get out of it? And the first thing I was thinking was that doing math really helps you develop critical thinking and reasoning skills. But that was also the most boring reason I could come up with. And of course, that's the reason why you take math in high school. But it's also not very exciting. But one of the more practical reasons for doing it is that it provides a good idea filter. So anybody who's watched the news lately has heard a lot about the healthcare debate. You hear a lot of things like socialism and killing your grandma and things like that. But when you get down to it, the healthcare problem and healthcare in general is really just a math problem. You have X number of people that are in the United States. Some fraction of them are going to get sick during the next 6 months, and it's going to cost some average amount to pay for that sickness. So we just spread out the average. By averaging over all people, we just get a rough estimate of how much we're going to have to pay for everybody. And it's a very simple math problem. It's not very complicated at all. So really, if we're going to solve things like this, it's helpful to just be able to go through the math and have a very informed public debate on things like this. So that's kind of the practical reason for doing these kinds of problems. And then the last one is really that it's just kind of a fun game to play. And I'll give you an example of what I mean. So I was at the original Spider-Man movie, and I was sitting there with a friend, and Tobey Maguire is on screen, he's shooting web and shooting web and shooting web. And if you look at it, the web's like this thick, and it's going 30 meters out from him. And the friend sitting next to me was just like, how much does he have to eat to produce all that web? And nobody ever actually sits down and takes the time to calculate it, unless you're a geek like me. But that's basically the types of things that I do. It's akin to doing, I imagine doing like a Sudoku or like a crossword puzzle for anybody else. So I want to talk a little bit about how exactly you would go about calculating something like the Spider-Man problem. And one method that you could use to do that is something called the Fermi approximation. So Enrico Fermi, who was an Italian physicist, and a little bit of trivia for you, half the particles in the universe are named after him. But he popularized this method of computing things to within an order of magnitude. The approximation bears his name. It's called Fermi approximations. And basically, he would go up to his students and say, tell me the number of piano tuners in Chicago. And of course, I can tell by the blank stare on your face that you have no idea how to do that. And that's basically what his students thought. But what he showed is that through very simple approximations, you can actually calculate this and just about anything else, just by starting with what you know and using very simple math to do these order of magnitude estimates. So the first step in this process is to use what you know or look up what you don't know. So I can start by saying, well, I can't figure out just offhand I don't know offhand just how many piano tuners are in Chicago. But I know roughly 5% of my friends, like 1 out of 20 of my friends owns a piano. If I go down my Facebook page, I say, well, this person's musical, this one's not, this one's not, this one's not. And 5% seems like a reasonable number. Now, you say, well, that you could be way off on that. And you're true, I could be way off on it. But I know that it's less than 50% of people, because that would just be like, half of my friends don't own piano. So it's definitely less than that. But I know it's also more than 1 out of every 200 people, because I know quite a few people with pianos, and it would be odd to have that few pianos. So I know that that's somewhere in the bounds of what you'd expect to be reasonable. And you basically go down the line, and you write down all the things you know. So the next thing is that if you have a piano, generally you get it tuned about once a year. Now, if you're very neglectful, you might get it tuned once every 3 years. But you're not going to get it tuned once every 30 years. So we're in the bounds of what's reasonable. You're also not going to get it tuned 5 times a year, because that would be very expensive. Unless you're somebody who really plays it often, and that most people are just getting it tuned 1 or 2 times a year. You go a little bit further, you say maybe a piano tuner tunes two pianos a day, and it's helpful to know the number of people in Chicago is about 3 million people. You could just look that up on Google, or you could know that roughly the number of people in a big city is about 1 million people, and Chicago is a pretty big city, so maybe it has a few million people in it. So these are all the things that you want to start off with. And the next thing you want to do is, just like you did in high school chemistry class, you just want to cancel units. So if I wanted to calculate the number of pianos, well, I know there's 3 million people in Chicago. I know there's 1 piano per every 20 people. So I just cancel units in the same way that I did canceling grams per mole or whatever you did in high school. It's the same exact thing. So 2 divided by 2 is 1, 3 divided by 3 is 1, people divided by people is 1. And then you just do that excessively. So people will cancel with people, pianos will cancel with pianos, years cancels with years, days cancels with days, tunings cancel with tunings, and if you multiply all these numbers together, at the end of the day, you'll get about 200 piano tuners in Chicago. So starting from absolutely nothing, you really can just build up and figure out a way to come up with a reasonable answer. Now you might ask, well, how do you know that this is anything close to the actual number? Well, if you look in the Chicago Yellow Pages, there's about 40 listings for piano tuners. So we're off by less than a factor of 10. And we're probably even a little bit better than that, because not every tuner is going to pay for a listing, and the ones that are listed might have several tuners in them. So we're actually pretty close in this regard. So next I'm going to get into what I hope will be some fun examples for you guys. And I'm going to start with a disclaimer. I just want to say these are all just estimates. I'm making no claims about their factualness, so please don't sue me if I'm getting anything wrong. And we're going to start with this guy, which I'm assuming most of you all know, but for those who don't know him, this is the Stay Puft Marshmallow Man. He is I suppose you could call him a character who appears in the last climactic battle in the Ghostbusters movie where he's trying to kill all of them. But the Ghostbusters movie leaves one question that's unresolved. How long would it take to eat it? So, again, you want to start with what you know. If you take a marshmallow, you know it's about 1 inch tall, maybe half an inch wide. So from that, I can calculate the volume of the marshmallow just by taking 1 inch by half an inch by half an inch. And if you look at on the back of a package of marshmallows, you can find that there are about 25 calories in a marshmallow. So, putting those things together, I can say that there's about 75 calories for every cubic inch of marshmallow. Now, looking at Mr. Stay Puft, he's about the size of a 10-story building. Each story of a building is going to be about 14 feet, therefore he's going to be about 140 feet tall. is going to be a little less than half of that amount wide. So we'll say 60 feet wide, we'll say 60 feet deep. And from that, I just multiply all those numbers together and I get his total volume, which will be on the order of 500,000 cubic feet. And I can also convert that to inches. So then the last part is, like we said before, just cancel the units, multiply calories per inches cubed by inches cubed, and you'll get the number of calories, about 64 billion calories. Now, if you take the FDA recommended 2,000 calories per day diet, you can calculate that it would take about 8,000 years to eat it. So this is a pretty fun example, I hope. And but I know there was a little bit of math there, and math can tend to lose people, so I want to hopefully get your attention back. So our next problem, we'll be talking a little bit about sex. And since you all work at Google, I can only assume that you're thinking one thing. But I'm here to tell you that there's more things in life than just coming up with the world's greatest search algorithms. So there's a problem with this one, with this calculation, in that it's hard to start with what you know, because there's many different types of people, and as you can see by the wide variety of people that I've included in this slide, some of them are going to be having more sex than others. In some cases, a lot more sex than others. But we need to come up with some numbers for this. So we're going to use upper and lower bounds to get a rough idea of where the average amount of sex that people are having. So the question we're considering is, how many people are having sex right now? Now, if I asked you, each of you, how often you have sex, each of you would give me a different number. Now, there's a lot of different people in the world. There's everything from babies to really old people. You guys all look like mostly you're in your 20s, and many of you are probably in committed relationships, so you're going to be having sex a lot more than most people. But that being said, the babies really bring the number down. So on average, people are probably not going to be having sex once a day. At the other end of the spectrum, the people who are having sex tend to have a lot of sex, so you're probably going to be having sex more than once a year. So on average, you'd expect that once a month seems like a reasonably good number. You know, it fits within the bounds of what we consider acceptable, at least by my standards. So the next question is, you want to ask, well, how long does a typical sexual encounter last? Well, 10 hours, at least if you trust your Viagra commercials, seems a little excessive. If your sex is lasting 10 hours, you should probably call your doctor about that. So that one's out. Now, if your sex is only lasting 10 seconds, we should probably just skip this one and just, we're not going to comment on that. So 10 minutes seems like a reasonable amount of time for a typical sexual encounter. So if you take 10 minutes and divide that into a month, get your units to cancel, you'll find out that people are roughly having sex 0.02% of the time. Or put another way, the probability that any of you in this room are having sex at this instant is about 0.02%. So if I take that fraction and multiply that by the 6.7 billion people that inhabit the Earth, you'll find that about 2 million people are having sex at any given instant on the planet. So I know what you're thinking. This is fun for marshmallow men and sex problems, but what you're probably thinking, is this actually useful for anything? So to answer that question, I talked a little bit about how can you use this in healthcare and government policy, but another thing that's been in the news lately is the energy crisis. How are we going to supply energy as we run out of fossil fuels, and what's a cleaner, more efficient way of doing that? So you might want to ask, well, how much area would it take to just tile some large section of desert with solar panels, and can we get do we have enough space to get all of our energy with solar power? So to do this one, most of us don't have facts about solar power just stored away unless we do research in that area. So it's helpful to do like a quick Google search just to find out some numbers, and doing that, we can find there's actually a mistake in this slide. It should be 3.2 times 10 to the 12 watts used by Americans. That's the amount of power that we use at any given time. And if you look up the amount of sunlight that's actually hitting the Earth, you'll find that there's about 650 watts per meter squared. So roughly the size of your windshield is getting hit with 650 watts of power every second, which is why your car, why your car gets hot if you park it in the sun for too long. So I can use these numbers to calculate how much power I'll get out, but unfortunately, even the best solar panels are only about 40% efficient, and this is even assuming that you have the best top of the line just coming out of the research labs solar panels. So again, you just do the messy math part. You take your 3.2 times 10 to the 12 watts that you need, divide that by the amount of energy that you're getting out, and you'll find that you'll need about 4,600 square miles of area just to power all of the United States, and that's about the size of Rhode Island. Now, obviously, the good people of Rhode Island probably don't want to give up their state just so we can power all the other states. So there's a lot of different people who are thinking about, where can you actually put these? And there's like a solar roads project where people are saying we should tile the roads with solar panels. But you can start to, when you have the power of these approximations at hand, you can start to think about how to solve these problems in a practical and efficient way. So I'm gonna do one more problem, and I'm going to end with the age-old question. This is also where my book gets its title. How many licks does it take to get to the Tootsie Roll center of a Tootsie Pop? So again, you want to start with things that you know. So I have somewhere in the deep, dark recesses of my pocket a Tootsie Pop. As you can see, Tootsie Pop is about an inch thick. So to get to the Tootsie Roll center, it's going to be about a little less than a centimeter to actually hit the Tootsie Pop. Now, if I lick it, you can tell it's been licked. As you can see, there's a little bit of, aside from the saliva, you can tell it just changes the shape of it. Now I'm going to hand this to you. So, yeah, go for it. That is all you if you want it and you think I'm healthy.
How do I estimate that?
Well, that might involve doing some Google searches to find out a little bit about my health background. You can just barely tell it's been licked, right? I mean, if I can hand that to you, you're not going to want to eat it yourself. So it makes sense to assume that the amount of material that I've removed from the surface of the Tootsie Pop is just the amount that I can see, just barely the amount that I can see. And if you look up online, the smallest, the resolution of the human eye can see things down to about 10 microns, which is about 10,000 times smaller than a centimeter. So all I have to do is divide the distance that I have to travel by the distance removed per lick, and I will get about 800 licks. Now again, you might want to check the factualness of this. And this is a true story. I had a friend in college who actually sat down and counted the number of licks it takes. Now, of course, it's going to depend a little bit on how big your tongue is, and how much saliva you have, things like that. But they got 900 licks, and I got 800. So I feel like I'm pretty close, definitely within a power of 10. So with that, I'm going to end here, and I will take questions from you guys, if you have any. That's a pretty good question. It was during my graduate quals, and the Fermi problem was just something that it was one of the problems on the qualifier exam, and I had just done enough of them and preparing for that I thought, hey, this might make a good book, and it was that and money.
Do you have any real life scenarios where you can estimate something that turned out to be really valuable and sort of more than just movies?
Yes, plenty actually. So whenever you're doing, I mean, this would be useful for you guys too. If you want to figure out how fast some search algorithm you're going to do takes, you always want to do some rough estimate of it. And in physics, a lot of times you don't know. You have very little information about where you're supposed to be looking for something. So an experimentalist will want to know where to set their dial. And to do that, the best way to do that is just have a rough estimate, order of magnitude estimate of where you're looking to see whatever phenomena you're searching for. And doing computational physics, that's something I do a lot. I try to calculate, in the introduction she mentioned that I study nanoparticles and nanoscale self-assembly. So if you're trying to get something to self-assemble, a lot of times it happens in a rare event. So you want to know how long your simulation is going to run. You don't want to run a simulation for months and months and not get any data and then never be able to get your thesis or a paper out of it. So it's something that I use in research every day.
So I think it's hard for human eyes to comprehend kind of the unit, right? So how much really is a mile? A mile, okay, you can kind of conceptualize. When it gets really big or really small, I think it becomes really difficult to trust some assumptions about, how many baseball players have pianos. I mean, that's kind of simplistic. But when you get to larger things, like how do you kind of get around that?
Well, the math is always the same, and the unit conversion is always the same. So it's the same math, but just with bigger numbers. But one of the things that I think if you do enough of these sort of problems is it gives you an appreciation. You get what I call, you start to build what I call numerical landmarks in kind of number space. You know that you can spend $1,000 a day with. If you have $1 million, you can spend $1,000 a day for like 3 years. But if you had $1 billion, you'd be spending $1,000 a day going back to the time of like Christ. So that you start to, big numbers and small numbers are just like anything else. Like once you work with them enough, you kind of, I guess, build a conception for how big they are. So another thing another example is the number of stars in the sky, or how big the universe is, or how long the universe has been around. And these are all things that physicists estimate all the time. And it's basically the same thing that they're doing there.
I have a question back here.
Yeah.
So one thing that we do a lot here at Google is we kind of try and forecast, what our advertisers will be spending, and how we may be able to get that impact and help build our businesses even more.
Mm-hmm.
So do you have any suggestions or tips on how how we could better forecast?
How to better forecast? Well, I don't know very much about advertising or business in general. But I think any time that you can sit down and say, you can set bounds on where things are going to be. If company X wants to sell this much product, and you have some rough idea of how many advertisements you're going to have to send out there until you're going to hit somebody who that advertisement is going to reach, then you can start to make some progress in terms of where you should be directing things. And this sort of approximation technique would definitely be useful for that, much like anything else. But as far as specific examples for how it can be useful, I'm a little bit at a loss just because I'm not familiar with that. Yeah.
Did math always come easy to you, or do you have some tricks that you sort of learn along the way that help simplify it for you?
Has math always come easy for me? Yes and no. I think you always learn tricks along the way, right? Your math teachers tell you that every number, any integer multiplied by 5 gives you a number either 5 or 0. There's always these sort of tricks for it. But I think for me, I think I was always pretty good at math, but anytime you can come up with a trick, it's useful. I can't point to anything in particular and say that was what helped me get over the hump. I will say that since I started doing a bunch of these problems, I've been able to conceptualize numbers a lot better than I was before. So I think it's been useful for that regard. In that regard. You dropped it?
I dropped it.
Now you're definitely not going to want to lick it. Anything else?
So do you always win the contest where you have to guess how many jelly beans are in the jar?
I always come pretty close. I don't always win. Usually they put it in some odd-shaped container to try to fool you a little bit. This is a great, if ever you're at a carnival, now you know how to guess the number of jelly beans in the jar. There's a funny story about that, actually. So I was at, like I said, I'm new to this whole author thing. So when we were going through different titles for the book, and actually one of the original book titles or covers that they had was this jelly bean jar filled, and just because that's like the standard problem that you can do this for. Well, the problem is that as we were going through titles, the title we really wanted to use was Great Estimation. It was something my friend came up with, and we thought it was like a clever pun. But it turned out that there was already a book on the market called Great Estimation. So I was telling some people about it, and they were like, don't worry, titles aren't copyrightable, you can get away with it. So then the first thing that my publishing company gets back to me with the picture with the cover is the exact same cover picture as the book that is already published called Great Estimations, and it was the jelly bean copy. So as much as I wanted to use that a jelly bean example, I just couldn't do it because there was already a book out there with it. I'll say one more thing. This is calculating stuff is pretty fun, and it's you can almost always get answers for questions. But I stress almost because there have been 2 or 3 problems that I could just not come up with a good answer for. And I'll throw this one out there, and if any of you can solve it, please let me know. So a friend of mine knew I was writing a book, and they said, "Yeah, I got a great problem for you. If you took all the fish out of the ocean, how much would it sink?" So if any of you guys can come up with an answer for this, please let me know, because I've not been able, I'm thinking, I could probably come up with an average size for a fish, but I just have no idea of figuring out how many fish there are in a population. If any of you guys can come up with any other way of figuring that one out, please let me know, because that's one that has been bugging me for years. The other one I can come up with, it was one suggested by my sister, and it was how many fireflies would it take to produce the output of a lighthouse? And I just could not come up with a way to estimate the amount of light coming out of a firefly without thinking that I was going to be really, really far off. So there's definitely, there's questions that I won't even attempt. Like, if somebody asks, what's the probability that God exists? It's not really a physical question. Philosophers have been dealing with it for centuries, and I am not going to contribute anything useful. So as long as it's a physical question, usually you can come up with a pretty good estimate for the answer. Yep, way back there.
Yeah, so have you ever tried to solve a problem and then realized you're way off, like after you actually looked at it?
Yeah, all the time. Usually though, it's because I do the math wrong as opposed to getting the method wrong. Like it's usually, because usually you can come up with a pathway to get the answer, and then you just make like a stupid math mistake. And then those are easy to correct. Occasionally you get, one of the assumptions that you made in the beginning is bad, but it's important to try to be careful with that, and that's usually the time that you're most skeptical about them, about the whole process. Usually you think, I can do math, I'm not going to make any mistakes there, and that's where you run into problems. So I have to ask, is this like, I remember being in school and they would have like, every once in a while they'd have a convention that you get out of English class. Is this like that for you guys? Are you guys like trying to come up with questions because you don't have to go back to work if you stay here?
I'd say that there are more people who didn't come because they're stressed out about the number of things that they can do. I think part of our corporate culture fault is not like we don't get out of stuff, right? We put bust your butt until 8 at night. So I think we're probably like the more prudent ones that are like making my work-life balance is in order. I can afford time to take a second to learn about something.
So,
Have you heard anything about our officer?
I have not, but I see the video arcade over there. I see the piano over there. I see what looks like some sort of drum playing kit over there. So I assume you guys are very busy and professional. Oh, so I'm going to estimate this. Well, given by the numbers of chairs here, let's say it's 6 by about maybe 10 rows, you could fit about 100 people in here. So I'm going to say maybe 100 or so people. 150 people.
Within a power of 10.
Within a power of 10? What's the actual number?
Around 250.
I think it's two. It's a lot of two.
150 and 2.
Yeah.
I'm going to be looking for a job soon if you're looking for more people. Built-in nanostructure. I'm not sure what that would you do, like a little mini Google. I'm not sure what nanostructures can do for you guys though. IBM does a lot of weird research stuff. They are pretty hardcore when it comes to fundamental research. I mean, they were the guys who were moving around individual atoms and spelling out IBM with it, so they're pretty intense. It would be harder to spell out Google just because there's more letters. So any more questions? Things you would like me to venture an estimate for? Yeah.
So this is kind of silly, but I feel like anyone who went through like the interview process here could attest to it. Sometimes these are questions that you get asked in interviews and of like these weird brain teasers, and I don't know, I still haven't figured out if it's meant to like throw you off and put you on the spot and like show how you solve a problem, or if you're supposed to be thinking outside the box. But I know one that I got was how would you estimate the number of cans of paint you would need to paint half of the houses in the U.S. blue?
Oh yeah, that's you can be pretty standard.
Yeah, well I guess what we hear about. Because I'm kind of curious if I was at least close.
Well, there's about 300 million people in the U.S. Presumably you can fit 4 people. You know, we'll say 3 people, make the math a little easier. 3 people per home, so that's about 100 million homes. And some people live in apartments, but we'll neglect that for now. And let's see, where would you go from there? The amount of paint. Well, I had a can of paint that painted basically one wall in my apartment. And I imagine an actual house would be maybe like anywhere from 10 to 50 sizes of that wall. So that gives you a rough idea of how much paint you would need per house. And then you just multiply that by the number of houses. So is that something close to what you said? See, cool, so you already know what you're doing here.
We'll see.
What is the blue, like, the blue, would you have to figure out how much blue paint is manufactured in the US, or is that kind of like it doesn't matter, it's just blue?
What?
See, now that's why we got the question wrong.
Did it have to be blue, or like did I have to take into account that there was going to be like a shortage of blue paint eventually, or is that?
Yeah, so actually the way I ended up answering was like saying that I would paint every single house, but only paint half the house blue, just because if you could figure out how much paint it would take to do a half of one house, then it'd be easier to multiply it out. But
Right.
no one would probably want half of the house to be blue, so I'm not sure if my answer was actually correct. No, I guess. We have some machine paint.
Where are the non-Michigan fans?
No.
You are not popular here, are you?
No, we've got a good group here. Green and white.
Yeah, what do you estimate?
What's that?
In this office.
In the office?
In Ann Arbor.
In our state versus university fans. Well, that would be hard to estimate because the state fans tend to be a lot quieter because they know they're outnumbered.
Not me.
Not here.
Not-
Not here, not in this office, I don't think.
Oh, when are they playing state?
October 3rd.
October 3rd, okay.
That's about the same
I wonder if they're going to be, is it as loud, are the Ann Arbor people louder out by state, like on campus, like are they just much more vocal? No. I mean, it doesn't really matter anyway, you guys don't count, only Ohio State counts. Them's fighting words.
I have one last approximation question.
Sure.
So the Google logo is the colors of Legos.
Uh-huh.
So how many Legos are there in the United States?
Oh, geez. That's a good question. Well, you mean ever or now?
Right now.
Right now. Well, you could say roughly 50% of the population is children, so that's 150 million kids. I know I had Legos when I was a kid, and since you guys work at Google, I'm going to assume that there's a large geek factor here. So I'm assuming most of you guys had Legos, but I'm not sure in general the population had. Let's say 50% of the kids have Legos. So I would say 150 million kids, 50% have Legos. And we're talking about individual Lego pieces. God, how many Lego pieces did I have when I was a kid? All right, well, I built things that were like yay big. So if you're taking Lego pieces that are this big, it'd probably be 10 by 10 by 10, so maybe 1,000 Lego pieces per kid, 150 million kids, half of those. I want to think about this one a little bit more, but I want to say on the order of 1 to 10 million Lego pieces. But it could get really, I want to think about this one a little bit more though, because it could get thrown off, because rich kids could have billions of Legos. So, I definitely need to think about that one more. That's a good question.
And they make big Legos now, where there's only 30 pieces, and those tops, those huge ones.
I always assumed that those were for
Yeah.
I mean, they're closer to Lincoln Logs, because you can't really do much with them. It's classic Legos or nothing for me. That's where I draw the line. And no Mega Blocks either. Mega Blocks don't count. That is the cheap Legos that you got when your parents didn't want to buy the actual Legos. That's all I got.
Well, thank you so much for coming, and